So the second day of integration by substitution, which is day 30, involves lots of examples of substitution and one final property. What's happening here is that if a function is even, you know that half of the function between negative a and a is going to be the same as the other half, so you could just go from 0 to a and double that quantity. For an odd function, which looks like this, you know that the symmetry causes part of it to be positive and part of it to be negative. So if I go from negative a to a, part of it will be positive, part of it will be negative. Those will cancel out and you wind up with 0. So applying that to this example over here, the antiderivative of the cubic function from 0 to 4 produces an area of 64. Drawing that would look something like this. Cubic, 0 to 4. And then the area underneath that is going to be 64. But because it's odd, we know that cubic would continue on and go down this way. So if I go to negative 4, I know that this area is going to be negative 64. So pause the video and answer these 4 examples quickly. And the directions say without using the fundamental theorem of calculus, which means you should just answer them using logic and the properties of even and odd functions, most specifically odd because this cubic function is odd. Okay, here come the answers. For part A, if we're going to go from negative 4 to 0 for x cubed dx, inspecting this diagram over here just means that the odd property says if 0 to 4 is positive 64, then negative 4 to 0 is going to equal negative 64. For part B, antiderivative from 0 to 4 of negative x cubed dx, I'm going to bring the negative to the outside. And now we know that this part here matches what we were given as positive 64, so that answer is negative 64. Part C, negative 4 to 4 for x cubed. Now we're including both parts, both the positive part from 0 to 4 and the negative part from negative 4 to 0. Those are going to cancel each other out. And a direct application of property 2 here is that that quantity is 0. And then finally, for part D, the antiderivative from negative 4 to 0 of 5x cubed, I'm going to bring the 5 to the outside, because constants can move inside and outside of antiderivatives. We know from a previous part A, that this quantity here is negative 64, so my answer is 5 times negative 64, which equals a negative 320. Okay, 2 more examples. I've covered up most of the answers, but I'm going to give you a little bit of a head start. First one, if you're given f prime of x equals negative sine x over 2 and the point 0.06, you're solving for y, and we want a specific solution. In other words, we're not going to have plus c. So I change f prime into dy dx. I move the dx to the right side, and then in order to solve for y, I need to undo the derivative. So the antiderivative and the derivative will cancel out, and we'll be able to solve for y. So you're going to pick it up from here. Pause the video and figure out how to do this. My 2 hints are 1, move the negative outside the antiderivative, and 2, x over 2 is a function inside of a sine function. So I would start with the x over 2 part. Okay, so there's the setup. I've moved the negative to the outside. The u substitution appears right here. X over 2 is going to be my u. The derivative of x over 2 is 1/2. So in order to replace all the blue writing, I need to have a 1/2 and a dx. The dx is there. The 1/2 is not there yet. So what I need to do is throw a 1/2 inside the function. And then to offset that 1/2, I put a 2 on the outside. So the 2 and the 1/2 cancel each other out. But now on the inside, I have everything I need. I have the 1/2 dx for the du, and I've got x over 2 for the u, so I can now take the antiderivative of sine u du, which is negative cosine u, and again, because we're given the point 0.06, we're going to substitute that in, find out that c is 4, and our final solution to that differential equation is 2 cosine x over 2 plus 4. And again, you could take the derivative of that and guarantee that it's correct. All right, second question gives an awfully intimidating function here, and you're supposed to solve for y and also use the given picture and the point 0.2 to figure out the particular solution for y. So hint number 1, separate the two functions, 4x and then the rational function, treat them separately. The first one, the antiderivative of 4x, is very straightforward. The second one, as you can see, the u substitution is let u be all of the stuff inside of the 3/2 power. U to the 3/2 or u to the negative 3/2 when you're bringing it upstairs isn't so bad to deal with. So u is 3x cubed plus 1. The derivative of that is 9x squared, which, oh look, we have upstairs. So our du, everything is taken care of. 9x squared dx is all there. So what looked like an awfully intimidating problem boils down to the antiderivative of u to the negative 3/2 du. Finishing up, antiderivative of x is x squared, 1/2 x squared actually. 1/2 times 4 is 2, so you get this statement. This is still in terms of u, so I need to turn it back into x's. And now once I have everything in terms of x, I'm going to substitute in our point 0,2. Lots of things disappear, and we wind up with c equals 4. There's the particular solution to that differential equation, and you could check it in decimals to get a picture that looks a lot like that. So final two examples are just more of the same. Behind this transparent owl is the solution to f prime of x equals secant squared 2x. And again, you're given the point pi over 2, 2. So turning fy into dy dx and moving dx to the right side produces this. Now you need to say to yourself, if I take the antiderivative of both sides, what derivative produces secant squared? So pause the video and try and finish that all the way through to the end. And here's the solution. 2x, the function inside of secant squared, is the thing that we're going to replace. Taking the antiderivative of secant squared isn't so bad, so I need to get rid of the 2x. U is 2x, du is 2 dx. I'm missing a 2, so I throw a 2 inside the antiderivative so that 2 dx becomes du. Secant squared 2x becomes secant squared u, but to offset the 2 that I put on the inside, I need a 1/2 on the outside. The antiderivative of secant squared is tangent. Substitute it in your point. Pi over 2 doubled produces pi. Tangent of pi, tangent is y over x at pi, which is 180 degrees. X is -1, y is 0, so you wind up with 0 here. So c is just 2, and your final answer is y equals 1/2 tangent 2x plus 2. Second example on the screen, find the area of the region shown for y equals that function. It's plotted over here. And the area, you have to kind of assume that this number here is pi. So you're going to go from 0 to pi, area under that function there. So setting it up, you have this. Again, I see 3 different functions, so I'm going to evaluate 3 different antiderivatives. Treat each of them separately. So again, pause, practice your trig, try and evaluate those 3 antiderivatives, and then look at the answer. So here's the solution. First one, inside the sine function is 3x, so I'm going to let u equal 3x. du is 3 dx. I need a 3 and a dx. To offset that 3, I did 1/3 on the outside. So now I have 3 dx is du. Sine 3x becomes sine u, and the antiderivative of sine u is negative cosine u. Turn the u back into 3x, and you have negative cosine 3x with 2/3 on the outside, evaluated from 0 to pi. I have a typo up here. This should be pi, not 2 pi. Change that into pi. Makes more sense now. Okay, second and third are very similar. Antiderivative of cosine 2x, let u equal 2x. du is 2 dx. I need a 2 here. I'm going to offset the 2 that I put here with a 1/2 on the outside. And then the antiderivative of cosine u du is sine u. Turn your u back into 2x and you get this. You should get used to how to deal with the 3 and the 2 in the arguments of trig functions. You just notice that if there's a 2x here, my answer winds up having a 1/2. And if there's a 3x here, my answer winds up having a 1/3 times whatever other constant was on the outside. So you'll get faster at doing those because they'll appear a lot. And then the last term, the antiderivative of dx is just 1. Substitute 0 to pi in all 3 of those. You get a bunch of statements that you need to evaluate. Again, practicing your unit circle trig, and you wind up with 4/3 plus pi is the final answer. So the exact area under the curve of this function between 0 and pi is 4/3 plus pi. Okay, substitutions are just something that you need to practice a lot. Keep doing the homework and you'll get very quick and very good at substitutions.